Hello everyone. In this video, we discuss feature engineering. Feature engineering is the process of transforming raw data or raw features into meaningful features that improve a machine learning model's performance. Techniques like normalization rescale data to fit within a specified range, ensuring consistent contributions from all features during training. Additionally, creating polynomial features allows us to capture complex relationships in the data by generating higher degree combinations of existing features. To explain the problem that we were working on, remember that we had a data frame about certain features of vehicles and their MPG as a measure of their fuel efficiency. And after doing some pre-processing, as you see here, we had the histogram plots, also correlation metrics to see whether some of these features are correlated so that we can work only with a small subset. We figure out that we can have a two-dimensional problem in a sense that we have two input features, horsepower and weight, and the goal is to find the relationship between these two input features and the MPG. And therefore, now if we have a new test data point with given horsepower and weight features, we can predict the corresponding MPG or mile per gallon. Something that we immediately notice here in this figure is that horsepower is in the order of hundreds, right? So it's a little bit smaller than 100 up to 200, 225. However, if you look at the weight features, they are in the order of thousands. So, the weight of a car is can be anywhere from 1,500 to 5, 6,000 pounds in general. And therefore, you can see here a big problem when we are working with problems like linear regression. And the fact that just because the weight feature is usually larger than the other features, or here horsepower, our model can become overly reliant on this weight and somewhat ignore the changes and the behavior of horsepower to find this relationship between input features and MPG. To explain this in a little bit more details, remember this is our data frame that we are working with. And we decided to work with two of these columns as input features. So this allows us to form something called data or feature metrics, which is of size n by 2. N is the number of observations, 2 is the number of features. And this is very standard across machine learning and data science libraries that the rows correspond to the observations or samples, and the columns represent features. And since we have only two features here, you can see that we have two columns. Similarly, we form a target or output vector, which is of size n by 1. And here we have the corresponding MPG for each pair of inputs that we have. So this is the general form of supervised learning where we have input and output pairs for our training data. And as we mentioned, one issue is that the model can become overly reliant on weight because this beta tool will have a bigger impact on the problem because these raw values of weights, you can see that they are greater than horsepower. And the question is, well, can we somewhat normalize or rescale the data so that horsepower and weight values, they are in the same scale or range? And there are multiple ways to do this. One way, which is very a nice way you learn in the statistics, is using the idea of z-score or standardization. The idea is that if you have a bunch of numbers here, let's say n observations, so these are the n observations, let's say for weight or horsepower, you can find the sample mean by just taking the average of these, and also the empirical standard deviation. And then you can transform each of these values, each of these features, by subtracting the mean and dividing these by the standard deviation. So now, given these original features, which I can just show them using xi, I from 1 to n, now we have these scaled or transformed features, which have this linear transformation in the form of xi minus mu divided by sigma. And the nice property of this type of transformation is that now these transform features have mean 0 and variance 1, which means that regardless of what the original distribution of data is, now we can have this mean 0 and variance 1. So with this in mind, now let's implement this. So as we mentioned, the first approach that I just discussed is called a standardization, where the idea is that given one original feature, I can subtract the mean and the standard and divide by standard deviation to transform this. But there's also another approach, which is called normalization. And the goal is to rescale features to be in the range 0 to 1. And in order to do that, it's a very similar idea. For each original feature, we can subtract that by the minimum value of all the features that we have and divide this by max minus min. So you can easily verify these that if x here is equal to the minimum value, then you get 0, which is the smallest value you can get in this range. But if we have maximum value of x, then you get max minus mean over max minus mean, which is 1. Here, we will show how to implement the first one, but they're very much similar. So the idea is that we're going to use the library scikit-learn, and also it is shortened as sklearn. So that's how you can import and use this library in Python. And inside scikit-learn, there is something called a pre-processing module. So as you guess, there are a lot of ways of pre-processing features inside this scikit-learn. And in this case, we import from scikit-learn.preprocessing a standard scalar. Remember, a standard scalar is a class, so you have to first instantiate these or create an object. In order to do that, we're going to use the default values. We create this object scalar. So now this doesn't have any information about our data, but we can provide our input or feature data matrix X and say that we want to fit and transform. So when you say fit, this means that find mu and sigma, mean and the standard deviation. And when we say fit underscore transform, then it means that also apply this transformation, subtract mu and divide by sigma. And something I want to show you, so I can just comment this for now. So once we do this, so obviously you can see that now these features have been scaled. They look much smaller than what they were. They were before in the order of hundreds or thousands. But now we actually converted this data frame into a NumPy array. So if for some reason you want to still work with data frames because you want to know what the first column is, what the second column is, you can do this by using the pd.dataframe method. So this means that we want to create a new data frame. Our data frame is basically these scale features, but we also need to know what columns we had. These are the feature names that we had. And we can do this because we already have the columns of the original data frame. So up to this point, we have not overwritten X, so we already have that information about column names. And if I run this cell, so you can see that we get the same exact result, except the fact that now has this nice data frame structure where I know that the first column is horsepower and the second column is weight. And can we verify that we correctly did the transformation? Yes, we can find the sum and the standard deviation across the two columns that we have. And we can do that using axis equals 0. So when you say axis equals 0, this means that we want to perform these operations column-wise. If it's axis equals 1, then we do them row-wise. And in this case, if I run this, you can see that for horsepower, the mean is very close to zero. It's 10 to the negative 14. That's for our purposes is completely zero. And the same thing with weight. And you can see that the standard deviations are both, in this case, equal to one as we expect. So this means that we correctly were able to apply this standardization pre-processing. Now, we can also look at something known as polynomial transformation. The goal here is to just give you a sense of different types of transformations or pre-processing that you can find in scikit-learn or sklearn. And one of these methods is that, well, once we have the original features, let's call this x1, x2. So x1 here represents horsepower, x2 represents weight. Now we can create higher order degrees of these combinations of features to be able to extract polynomial types of relationships between inputs and outputs, right? Because you know that in general, like let's say if your output is y equals x1 is a linear function of x1. But now if you have like x1 squared, x1 cubed, and so on, then you have these higher order terms. And we can do this easily using polynomial features from scikit-learn pre-processing. So you can see that in this case, very similar to the previous case where we have a standard scalar. First, this is a class. You need to instantiate this. And one very important parameter here is that you have to set the degree. What's the maximum degree that we're going to have? If it's degree 2, then we put degree 2. If it's degree 3, then we will have x1 cubed, x2 cubed, x1 times x2 squared. So we have to consider all combinations up to the given degree here. And for this case, I'm going to put this parameter also include bias equals to false because otherwise we will get 1 here as like x1 raised to the power of 0 or x2 raised to the power of 0. But we don't really need to consider this because once we fit this to a regression model, we already include that bias term. So that's why here I specifically say that I do not want to have a bias term. And once you instantiate this object, now you use again fit transform. So this means that find all the degrees that I need to consider and also apply this to the data that we have. And one very nice feature about scikit-learn is that also it will give you the names of the new features based on how it will calculate these cross terms. So in order to do this, you use poly. So poly is the name of this object that we have. And it has a method called get features name out. So this means that what are these names of new features where we have cross terms? And you only have to provide the names of the features that we provide to these polynomial features. And once again, I use pd.dataframe to create a data frame and use these column names that I have just found. You see that now we have horsepower and weight. So these are our original features that we have after applying a standard scalar. But now we have horsepower raised to the power of 2. So that's this number raised to the power of 2 and so on. And the same thing with weight square. That's the square of the weight features. And also we have the cross term, horsepower times weight. So you can see that now this way we can easily create these new features. And what is nice is that now we can actually think of this as a linear regression problem. How does this work? So we have horsepower and weight, and also we have these higher order terms or new features. And the fact that really matters is that in terms of these betas, these are the parameters that or coefficients that we have to find in order to solve the regression problem. In terms of betas, this is a linear function. There's no beta raised to the power of 2 or raised to the power of 3. The only things that are raised to these higher order terms are these features, and these are given. So we are not optimizing anything over those things. Those things are given to us because we have the horsepower and weight values, and we can find all these higher order terms and see what the actual values are. And once you plug in into these weighted sum or linear combination, this is very much a linear regression. The only difference is that now you have to find a larger number of weights or parameters. And you can see this way you can have a regression problem that is able to find more complex polynomial type relationships.